Again, good morning and welcome to the Innovation Exchange and today's webinar, Optimizing Existing Rooftop Unit Efficiency. I am Megan Hoy, the Engagement Coordinator for the Innovation Exchange and your moderator this morning. Just a few quick reminders before we get started. Please make sure that your microphone is on mute, whether you're listening in through your computer or the phone. Also, you should see a Q&A dialog box on the right-hand side of your screen or an orange arrow that can help direct you to it. I encourage you to enter questions that you have throughout the presentation as they come to you so we can address those topics and that no important questions aren't forgotten. If you have other clarifying questions that arise during the presentation, we'll try to answer those as we move through. Otherwise, we'll try to address them at the end. The Innovation Exchange is the research and dissemination arm of the Center for Energy and Environment, creating opportunities to communicate research and knowledge to energy and building experts through webinars, forums, blog posts, and social media, as well as other tools. If you have not visited us on the CE website before, you can navigate to our portal from the home page and enter the Innovation Exchange to learn more about the policy and field research we are conducting, the engagement projects we're involved in, and other tools and resources we are developing, including webinars and events. If you are interested in getting field and policy research updates and learning about upcoming events and resources, our free newsletter will deliver this information to you on a monthly basis. You can find the sign up in the upper right-hand corner on any of CEE's web pages. The Innovation Exchange engages in a wide variety of direct energy research as well as air quality, combustion safety, and ventilation research that is highly intertwined with energy use and healthy environments. Currently, we have a number of projects in progress. At the top of the list, you'll see projects such as improved effectiveness of commercial ERVs, condensing boilers, and you can see the rest of the list there, but are looking at commercial HVAC systems, ventilation, and the optimization of other specialty building systems. Also, we're looking at two projects focused specifically on ventilation and envelope aerosol sealing in multifamily buildings. One project is looking at air quality and the effects of secondhand smoke in vehicles. And we have a kind of a family of DOE Building America projects going on through the North Star Building America team, which is one of a handful of teams across the U.S. We're applying our expertise in the residential energy systems and combustion safety across these four projects. Recent projects that have been completed or that are nearing completion include those that you can see on the right-hand side of your screen, so window retrofit technologies, large building air leakage, tankless water heaters, heat pump water heaters in Minnesota, the optimization of existing RTUs, which we'll hear about more in a moment, and we'll have up on our website later today, and the combi systems. Also of note, the tankless water heater, we do have that final publication available on our website. The Innovation puts on a number of webinars each year, so stay tuned for upcoming field research and policy webinars that will be starting up again in early 2015. This morning, I'm happy to introduce you to presenter and longtime CE expert and the Director of Engineering Services, Mark Hancock. Mark has 25 years of experience in institutional, commercial, and residential building energy efficiency with an emphasis on building automation, field diagnosis and HVAC systems, and deployment of data logging systems for documentation of system performance. Mark leads the existing building commissioning team here at CEE, which focuses on improved energy efficiency in commercial and institutional buildings. He has extensive expertise in building system operations, optimization, and diagnostics. He has performed multiple existing building commissioning studies that have resulted in peak operation, reduced energy cost, greater occupant comfort, and improved ventilation. Mark has performed extensive hands-on measures of HVAC systems that have included airflow, water flow, verification of accuracy of building automation points, and sub-metering of individual systems. From 2009 to 2014, Mark gained experience in building commissioning as the program director for the Public Buildings Enhanced Energy Efficiency Program, otherwise known as PBEEP. PBEEP has reached 30 million square feet of state-owned buildings and has identified over $1.5 million in energy savings in these sites. The research that will be presented this morning was funded in part by a grant from the Minnesota Department of Commerce through the Conservation Applied Research and Development Program, otherwise called or known as CARD. So without further ado, a little introduction for today's webinar and on to Mark himself. Heating and air conditioning account for over 25% of energy use in commercial buildings, and rooftop units serve 40% of the floor space with those buildings. Upgrading to more efficient model is often expensive, and even for replacement of older units does not achieve the savings necessary to justify the investment. So what cost-effective options are available for building owners interested in reducing their building's energy use? One potential cost-effective option, especially for small businesses, is to retrofit rooftop systems to improve efficiency. Application of new technologies such as variable speed drives on indoor fans and compressors have shown promising results with improved operations and better control. The Center for Energy and Environment has conducted field research on the performance of retrofits to better understand their appropriateness and cost effectiveness in the Minnesota climate specifically. So thank you very much for being with us this morning, Mark. I'm going to hand it right off to you.
Thanks, Megan. You've given me a pretty short window here, so I want to get right into it. I'm going to give you a little bit of the highlight of what I'm going to discuss here. I'm going to first characterize the market for rooftop, or why rooftops are good potential candidates for optimization. I'm going to talk about the 3 optimization packages that we looked at as part of our study, and then we'll review the results of our findings. So why rooftops? Rooftops account, as Megan has said, they account for 25% of the typical energy use in commercial spaces. And they are typically used on a wide variety of spaces. Beyond lighting, rooftop units or heating and cooling units are the next biggest thing that are seen in commercial spaces. Again, 46% of commercial spaces use rooftop units. This is characterized by the CBEX data. And the information that it gives us shows that it's 2.7 billion square feet of commercial retail floor space. And that data is dated at 2003, but it's obviously much higher now. Rooftops have a wide variety of applications. They're in the commercial, manufacturing, industrial, retail, medical. They're across all different segments. And to show you that, I've included a couple of images that I've captured off from Google Images to kind of show you the wide variety of space uses that you see. In the left-hand side there, we have a typical fast food facility. It has 5 RTUs. On the right side, that's a 2-story small medical building. It has 6 RTUs. This is also applicable across the big box retail sites. This is a Sam's Club. They have 20 RTUs located on their facility. And if you further cast this across into manufacturing, this is a manufacturing facility that we've been working on. It actually has 50 RTUs on it. So you can see RTUs are used on a wide variety of space types and applications. So why do we use RTUs? Well, RTUs they're basically a one-size-fits-all application. They are package units. They are integrated with heating and cooling in a single unit. You can very easily put these on the roof and add ductwork in order to accommodate additional space heating or cooling requirements. They are very reliable. Again, you just pipe to them gas. In the case of the Minnesota market, we typically see a lot more gas heating than heat pump. But if you pipe gas and electric to them, they will run, and they typically run really bulletproof in our environment. They have a low initial cost. They come in a wide variety of sizes that meets requirements. And the real key is that there's a network of trained installers out there that can service these products over the life of the systems. So you're not tied to one person to maintain your heating and cooling system, in this case RTUs. So I was starting to think a little bit about RTUs and the history of RTUs and where they've come from, and I tried to draw a parallel to the cell phone industry. With the recent release of the iPhone 6 and all the features that it has now, you look at the evolution of the cell phone, you come from a pager and you come all the way up to the latest version of the newest smartphones. That's quite an evolution of opportunity and options that are on those systems. If you parallel that to the rooftop market, this is all I could come up with the evolution of the rooftop market. We've gone from a simple thermostat to essentially a thermostat that has a time clock on it that will turn it on and off or change the set point based on a schedule. There isn't much evolution beyond that. So what's the problems with RTUs? RTUs generally operate inefficiently. They are standard efficiency from this factory in both the heating and cooling. They are typically constant speed. There's really no options for advanced controls. When you go and pick an RTU from a supplier, you generally get the standard efficiency on both heating and cooling. And if you're opting for something more high efficient in the new purchase or the replacement, you're probably going to have to wait a while in order to get that, which typically doesn't happen in the rooftop market. You're going to have to replace something and you have to do it quick. So there's really not a wide variety of options out there. Generally, a lot of RTUs also lack maintenance, which again affects their performance, but those that do maintain them can get a slightly better efficiency out of them if they're maintained regularly, but they are generally inefficient. The compact design also results in challenges for controls. The fan is located very close to the outdoor air damper, and as soon as you open the outdoor air damper, you get a large amount of outside air, which could affect the swing of the discharge air temperature greatly. So these small packages and close proximity to airflows don't lend themselves very well for control. The standalone control of rooftop units does affect their efficiency also. There's a lot of conflicting neighboring RTUs that don't have appropriate set points. Generally, it is one thermostat to one RTU, and the thermostats are not coordinated perfectly. And a lot of times that's what we see. Schedules, if they're used, don't match the requirements of the space, and there's often an oversizing that's happening in the RTU market, and that's again a result from just a pick and place from the manufacturer. We need a 7-ton unit. They don't have a 7-ton unit, but they happen to have a 10-ton unit, so we'll put that on. So oversizing and pick and place is another problem with RTUs. So what we wanted to do is study the potential for savings in the RTU control strategy. And the goals of our study were to evaluate the RTU control strategies for effectiveness, efficiency, cost effectiveness, and also to document the savings for a large-scale delivery of a conservation improvement program offering in the state of Minnesota. We wanted to confirm other savings found by projects that mimic our study. There have been a number of other projects which I will cite in further slides that document the cost savings for these optimization packages in other climates, but we wanted to see what are the savings in the Minnesota climate, because Minnesota climate is definitely more heating dominant than a lot of the other climates. So our goal was to collect information on a 60 rooftop units, and we wanted to span a typical winter and summer conditions in Minnesota. So I want to do a quick overview of the 3 rooftop optimization packages that we looked at. By no means am I taking a deep dive into these 3 packages. I'm just trying to hit the high points of these optimization routines so that you can get a better idea of what they have and what they offer. I'm not citing all the options for each one of the ventilation optimizers. So the first one we had in our program was the premium ventilation. This is a unique package in that premium ventilation itself is not a manufacturer based control or optimization package. It's more a sequence of operation that can be applied to a number of different manufacturers of thermostats. This is a package that is generally just the optimization of the economizer, the set point, and the meeting the needs of the space. And it's done in a way that uses an intelligent thermostat that has the capabilities of taking over the control of the economizer and measuring much more information about the space. Its features have demand-controlled ventilation, optimum start, and then occupancy-based set points. In our study, we used the KMC controller for the implementation of the premium ventilation. This is a screen that shows sort of what are the key components of the premium ventilation. It really is a below-the-roof installation control strategy. The thermostat in itself is a small little building automation system, as it were. It has the ability to take inputs from a number of different sources and take those inputs and make intelligent decisions on how the rooftop unit should be controlled. So as you can see from this diagram, there's an outside air temperature sensor, there's a discharge air temperature sensor, and then they take control of the economizer damper so that they can do better economizing. And then at the unit itself, it's measuring CO2 and then typical parameters that you would have on a thermostat, such as temperature and also humidity. And then also with that, they implement a occupancy sensor so they can tell when people are in the room or not. So if people are not in the room, you can set that temperature back to a more of a standby control. And as you can see in the middle, the RTU receives its typical signals for fan, cooling, heating, and other opportunities or other control strategies for the unit. Again, as I referenced, we used the KMC thermostat. This is a picture of one of the KMC FlexStats. This particular FlexStat in the picture does not have a little occupancy sensor, but there is an occupancy sensor that sits right in the little area to the lower right of the thermostat. And as you can see from this screen, it takes in a number of different inputs and is able to control the system. The unique thing about the KMC thermostat also is that you have the ability to daisy chain these together and make a building automation system out of this if that was the interest of the owner. The second technology we looked at was the Digi RTU. The Digi RTU is a VFD-based optimization package. They use a single VFD to control the speed of the compressor in the supply fan, and they have also demand-controlled ventilation and fault detection. I just wanted to include a picture of what some of these optimization packages look like. In this case, this shows some of the evolution of the Digi RTU optimizer. In this upper left-hand corner was one of the first versions that we received from the manufacturer. We implemented it at our site prior to really getting going on the research project. So that was sort of our test case. The picture in the upper right is the installation as we got from the manufacturer for the study, which included, again, a very big box, and then we had some of our own controls that are enabled here. You can see our data logger. And what they've done now is they've moved the evolution of this optimization package into the lower left-hand corner, that all the controls and all the drives are mounted internally to the system. And this is just a picture of the components that you can get in the lower right. And to better describe the operation, we've come up with this animation. And this is a standard animation for a standard operation where you have 100% fan speed, and as the space temperature increases, the only option for the rooftop unit to meet that demand is to turn on the compressor at 100% speed. So you can see from those little bar graphs, we have 100% compressor and 100% fan. And what happens in this situation is that if the rooftop unit is sized appropriately, it will run for a set amount of time and then turn off. If it's oversized, it'll turn off quicker. So as you can see from that narrative there, it's driving the indoor air temperature down. It gets down to a point where the set point is reached, and now the only thing that the rooftop unit can do, rather than cool off the space too far, is to turn off. And that's depicted by the 0% fan speed there. Note that the indoor air fan is still running at 100%. It's still pulling out outside air and return air at the same time, which can affect the discharge air temperature by going up and down in extreme weather conditions, whether it be hot or humid or cold climate. In the optimized operation, this animation shows that we start out with a fan speed that's much lower, so we're still moving air in this situation, but the fan is running at a slower speed. Once the thermostat identifies that we need cooling, then the fan and the compressor come on to some set speed. We've just arbitrarily said that it's going to come on to 75% speed, and now it's conditioning the air and cooling the space in a goal to try to drive the space temperature down. Once it gets to the point where the space temperature meets the set point, the VFD then tries to slow down the compressor and the supply fan at the same time, thereby keeping the system running and conditioning the outside air and return air at the same time, but conditioning it at a much lower level. The goal of this optimization is to try to keep the unit running as much as possible and stop the starting and stopping of the compressor and the fan at the same time. There is a point though when the system will reach its set point temperature and it doesn't have anything better, or doesn't have any other option rather than to turn off the compressor. But in this scenario, the compressor and the fan run at lower speeds for much longer time, conditioning that air and not resulting in those temperature swings in the spaces. So the last optimization package that we looked at was looking at the catalyst controller from Transformative Wave. This was a optimization package that was added a little late in our process, but we were able to fit it into some of our test sites. The catalyst controller is a VFD based optimization, but the VFD is only applied to the supply fan, and it's sort of a meeting between the Digi RTU and the premium ventilation in that it does a VFD solution for the supply fan, but then also takes over the economizer and makes better decisions on how to economize and integrated economizing with cooling. And the Digi RTU is also has an interface on it that enables you to see what's happening at the roof with a web connection. Interesting too that the Catalyst comes with a number of different options that you can select to just have a standalone Catalyst controller on the roof and not have a portal into that rooftop unit, or you can have that be connected to your internal network at your facility, or you can opt for a cellular connection, which is the connection that would give you all the options going forward. So it does have a stepped approach towards its deployment. This is a picture of the Catalyst controller. It's a small box that's mounted to the side of the unit, and they establish essentially a Wi-Fi network at the roof level in order to communicate across all the rooftop units. And you can see in the left picture that there's 2 units there, and there's 2 Wi-Fi antennas. These are both pointing back to the cellular connection that allows you for roof access, or web access. This is a little bit of an outdated picture of their website, but this is the kind of information you can get from their web page looking at how the units are running. So it'll show you return air, supply air, It'll tell you the outdoor air temperature and what the damper was doing. Interesting enough, on this particular one, you can see that the controls, signal from the controls where the thermostat is calling for cooling, but the catalyst had decided, I'm not going to do cooling, I'm going to do economizing. So it interrupted that cooling signal and allowed for the outdoor air to provide that cooling. So that's the example of some of the integrated cooling capabilities. So what are the manufacturer's claims? Premium ventilation, I went to their website. Well, again, premium ventilation doesn't really have a website, but one of the people that developed the sequences, Reed Hart, had written a number of papers, and they claim an 18 to 44% reduction in HVAC use. Digi RTU, on their website, they claim 40 to 60% reduction in energy and 30 to 60% reduction in demand. And then from the Catalyst website, they documented a 25 to 50% reduction in energy use. So what does that really mean? Can we get those kind of savings in Minnesota? I did a quick search on the number of research studies that are looking at rooftop units right now, and this is a little bit of an outdated picture of what's going on out there, but this was captured from the eSource website. You can see there's a number of different research studies going on, primarily looking at the catalyst, but there are some in there that have the Digi RTU. And if you see, there were basically 3 studies that have a pretty high number of units in there. The Bonneville Power Administration, our particular study, which is the 3rd line, and the PNNL study, which had a goal of 120 RTUs. The reality is that our study increased our number of RTUs. We were up to 66, and the documented number of RTUs from the PNNL study was 66. So that constitutes basically the 2 biggest studies that we know of right now, looking at RTUs and the optimization of RTUs. Another interesting thing that you can see from this is that the location of a lot of these studies are definitely in an area that's not consistent with Minnesota's environment. And to show that, I've included the climate zone map, and you can see that a lot of those studies were being performed in the number 3, number 4, and number 5 climate zones. And to my knowledge, there wasn't any documentation of savings results for those optimization packages in the number 6 climate zone that we are in. So that was the goal of our study, is to see what are those savings that result. So I want to give you a little picture of the sites that we used. We had 6 primary sites that we used for our study. They were a mix of office, light manufacturing, printing, lab, assembly, conference room areas. We had a large cross-section of types of space. They had the typical schedule of Monday through Friday, with slight variations in start times and end times, but there wasn't really any third shifts. There weren't any 24-hour operations. And then we added a site in the very end because we had a loss of one of our sites due to a lease issue, and we decided to add one site that was a limited number of, or a limited view of data, but we included that in our results to show you some of the information, just to make the data set a richer data set. We collected data with an internet connected data logger. The data logger provided 2 things for us. It collected the data for the performance of the unit, and it also applied the control for the unit. We deployed a flip-flop test protocol in our testing that allowed us to capture 2 years of data in a 1-year time span. In previous studies, we've seen a lot of people are doing the study of the building for a year to characterize the building, to understand how it uses energy, and then they implement the control optimization package and monitor that same building in the 2nd year to see what to document the savings that were as a result of the optimization package. The 2 flaws in that theory are that you don't account for changes in weather and changes for occupancy or anything that's happening in that facility. So we deployed a flip-flop test protocol that's depicted in that lower line. We switched between standard and optimized on a weekly basis in order to account for those occupied changes, those production changes, and staffing changes. And our internet-connected data logger was capable of doing the weekly switch between standard and optimized. As you can probably think about this, is that that required a lot more controls and hardware in order to facilitate that flip-flop testing, but it was well worth the money for us in that we were able to compress the time frame on getting that data collected. So our data collection period was originally identified as we wanted to get the units in and collecting data in early May of 2012 and complete the data collection period very early in 2013. But if you recall, the summer of 2012 was one of the hottest summers on record, and we had a number of delays in getting our optimization packages installed. So we had to modify our test period quite extensively in order to accommodate some of the problems that we occurred in our test. We actually collected data on performance starting from March of 2012 and continuing on through August of 2013. That was just the data performance of the units. The optimization packages were installed starting in June of 2012 and were removed in August of 2013, with the last optimization package really getting installed late in August, which resulted in that miss of the summer weather in the Minnesota climate. So this is another picture here of our test sites, the 6 that we had, the date that we started monitoring performance of the units, and then the date that the optimization package was installed. And you'll see that the line on the second from the bottom of that first table, the MDH site was the last one to get the optimization package installed, and because of a lease issue, it was the first one to be removed as a result of the tenant leaving the space. But we were able to capture enough data to make significant or substantial data on that package. And then you also notice that the Yale site, the YAL site, was only monitored during the summer, and the optimization package was not monitored into the dead of winter. So there's only summer data on that particular unit. This is a graph of the distribution of the rooftop units that we monitored. It's sort of the typical what you see in the commercial market. There are some anomalies in the lower end. We did see a 2-ton unit, which is rather not a typical unit, but the 4 to 15-ton market is definitely where you see most of the rooftop units deployed. So our analysis, our primary objectives of our analysis were to estimate the electric and gas use with and without the optimizers. We wanted to estimate the savings from the optimizers and compare those savings between technologies. We wanted to estimate the savings at each site, if there were indicators at a given site that made one technology better or worse than the other. And then we wanted to calculate a simple payback based on the installation of the systems and the measured data. And as I referenced before, the installation costs were something that we definitely needed to document, but the actual installation costs, we did not use that because of the fact that we needed the flip-flop, the additional equipment required for flip-flop testing. And the last thing we tried to do is develop a savings calculator for the state of Minnesota, which will be available. It's just a spreadsheet, a Microsoft Excel spreadsheet that if you give a particular site and characteristics of your facility, it will develop a savings estimate for whatever technology you select. And then the last thing we want to do as part of our study is to assure that when we were doing our savings and implementing these optimization packages, that we didn't compromise the indoor air quality or change the comfort with this at the site whether the optimizer was enabled or not enabled. So that's something that we definitely documented, and I will show you. So here's the electric savings for the units themselves. Catalyst achieved just under 30% energy savings. The Digi RTU was slightly higher at about, well, the Catalyst was 28%, the Digi RTU was 29%, and the premium ventilation was 15%. The interesting category here is the none category. There were a number of rooftop units that were not capable of being optimized, and we monitored those for their consumption patterns to see if they increased or decreased their energy use as a result of the optimization packages. And in all cases, the units that were not optimized did use more energy, which is a significant finding from our results. If you look at the baseline consumption of each unit by technology, this is not ideal, but it's something that I guess we had to deal with. The Catalyst product did see baseline consumption on their units much higher than the other two products, but you know, it does show that there are savings across units. So with the 28% savings that we saw on Catalyst and the 29% savings on the Digi RTU, and the smaller savings of 15% on the premium ventilation. The gas savings was something that was not exactly expected, but it was in line with what we've seen in other studies. The gas, in every case, the installation of the optimization packages resulted in an increase in gas use. In the case of the Catalyst, it was a 10% increase. The Digi RTU was about 7 or 8%, and the premium ventilation was around 5%. And you also see, again, that category of the none, the units that did not have optimization packages, they also had an increase in energy use as a result of the optimization packages. This is a more flatter curve as far as what the baseline energy use was in each optimization routine. The Catalyst, again, is at 10%, Digi RTU 7.6, and the premium ventilation at 5.2. To show you the energy saved by site, I've indicated each site here with the bottom telling you what optimization package was installed at each site. So you can see across the sites they achieved savings on electrical side that vary by site. And a lot of that has to do with the site, the way it's configured, its load that it sees from external, whether it's seeing a lot of outdoor perimeter walls or its interior. And if you want to see the site, or this is the electrical savings actually from the YAL site. And again, this was for summer only, so it's not showing the winter savings, and the confidence intervals are much larger for this particular one. So this is a limited data set, remember. This is only for the limited summer data, and this is only for the Catalyst controller. The gas savings by each building, again, it does vary, but you see the premium ventilation at the MDH site had just over 10% increase in gas. In contrast, if you look at the NUR site, that is the fourth one from the left, it actually had a savings of gas, but it had a much higher confidence interval. So there wasn't much we could say exactly about whether those savings could be applied across each technology, but on average, gas use did increase as a result of the technology. So in order to assess the economics of the packages, we needed to come up with a cost associated with installing these packages. And as I had referenced before, we could not use our exact costs in our study due to the requirement of the monitoring and controls. So we developed this standard 3 sites that have a varying number of units that are installed in it. So we came up with the small, the standard, and the large site category, and we had a varying number of rooftop units and cooling tons that are associated with each type. And then we asked the manufacturers and calculated what the cost would be on the case of the premium ventilation based on our experience in installation of the premium ventilation package. So you'll see on the first table there the estimated costs are just total cost at the site, with the Digi RTU having the highest cost for the larger sites, and then the catalyst having higher cost the more options you add to the catalyst controller. And the premium ventilation was in all cases the lower cost installation. So if you break that down by the number of units, oops, I got ahead of myself there. So the previous one was the breakdown by cost per unit, which again normalizes it, and if you can see there is an economy of scales when you start going for more units for each technology. The cost for that unit will get, or the implementation of that optimization package will get lower. And the last table we did look at the cost per ton, and these three definitely mimic each other, but they are definitely they review, or they reveal the costs associated with installation of these particular packages. So we applied these particular costs with the savings numbers in order to calculate the paybacks for these products. And these are the payback, or the cost effectiveness for these products. In each case, the catalyst product was in that 5 to 10 year payback, and the premium ventilation was across a larger payback criteria which spanned from 5 to 30 years. And the Digi RTU, being one of the packages that showed the most savings but also had the most cost, fell between that 15 to 25 year payback. So we also graphed this as a product of the baseline energy use, and as you would anticipate, the more energy you use, the better off you'll be as far as paybacks for these particular products. And to show you where we fell, this measured, or this shaded area is where the measured data really fell in our data set. So I also wanted to show you a little bit how it varied by groups. The rooftop units were grouped by their proximity to each other, and I don't want you to take away this as gospel, but I just wanted to show you that we had a number of groups that achieved higher savings in the 60% range, but we also had a number of rooftop units that did not achieve savings. This is a snapshot of a number of the groups that we had, and then this is another snapshot, and you'll see we had actually a negative 100% savings on one of the groups of units. So there's wide variability in these savings estimates. To assure you that we were controlling the space appropriately in both the basic and optimized control packages, we did box and whisker plots of the space temperature during the monitoring period, and in most cases you see that the standard operation or basic operation and the optimized operation were very much in line with each other. This particular case in RTU 9, at this particular site, there was a temperature difference in the space, but it was about 2 to 3 degrees. But that particular site too had a tendency to play with their thermostat a lot more than the other sites. Also, to reveal that some of this did predict exactly what we were anticipating we would see also. So these are box and whisker plots of the ventilation, or excuse me, the space temperature in the space for the premium ventilation package. And in most cases, this is exactly what we anticipate what the premium ventilation is supposed to be doing, which is setting the temperature back when people are not there. So this originally, this kind of struck us as maybe we weren't controlling to the same temperature, but in all cases we were controlling to the same set point, but premium ventilation was doing what it was supposed to be doing, which was setting that temperature back during times of unoccupied or no occupants in the space. And then for the indoor air quality, we were kind of lucky in that respect that our indoor air quality for all of our sites was never really in jeopardy. We did not have high occupant densities in any of the sites, and both the advanced and the basic operation in all the sites achieved the same amount of indoor air quality, so there was no degradation of indoor air quality as a result of the optimization packages. So the key findings that come out of our report are that all technologies achieve significant electrical savings. Gas savings were negative or statistically insignificant in a lot of the cases. Savings were highly variable, as you can tell from that previous graph that had all the different groups that were in there. And then the fan and the outdoor air dampers were not consistent from unit to unit. And we intentionally left the outdoor air dampers and fan settings the way the occupants would head them as we found them, because we wanted to test this as a real life scenario. And as I indicated in the cost effectiveness, that the larger units will achieve more cost savings. So these advanced control optimization packages did not achieve what would be regarded as cost effectiveness in a typical scenario for commercial building owners. They're not willing to accept a 5-year payback, so there needs to be some co-funding that's available there to make these more cost effective for them. The interesting thing I think we found also was that our control units were affected by the optimizers. The key finding there is that all the rooftop units need to be optimized at a site if you are to achieve the savings that are predicted for a given unit. If you get one unit that gets 30% savings and one unit that doesn't get 30% savings, you're not going to get 30% savings at the site. You're going to get something much less than that. And I think it shows from the data there that one size does not fit all for these optimization packages. It definitely depends on the space and the situation that's happening in that space. And an interesting thing too, that none of the products that I'm talking about right now that we tested are really available from the manufacturer anymore. The Catalyst has moved on. They have a number of different options and advanced control strategies that they've put in. Digi RTU, as I referenced in the pictures, they've modified their installation so that the market is moving very quickly. When we started the project, we had approximately 3 or 4 optimization packages to pick from as part of our research. I think there's probably 10 to 12 on the market right now. It's something that's very fast, rapidly moving product. I think one of the key things too with our study is that contractor support is very critical to the success of the products. You need somebody local that can support the products in the event that you're going to have an issue with the system. And I will reference the fact that all the products that we tested in our study had issues with the Minnesota climate. A number of them had issues with the extreme cold. A number of them had issues with fine tuning. If you were to install the product in the summer, could you be assured that it was going to work appropriately in the winter? So contractor support is very critical to these products. So with that, I think I'm going to try to tie this up. I am trying to be conscious of your time. We are approaching 10 minutes to the end of the hour, and I wanted to leave it open for the possibility of questions. So I'd like to thank you for attending the webinar, and at this point we will turn it over to questions.
Wonderful. Thank you, Mark. That was a great overview of the technologies and the findings. I think we'll just start off with 2 quick clarification questions that were asked earlier on during the broadcast. Does the Digi product have an internet connection?
The Digi product that we tested did not have an internet connection. I believe they are working on an internet connection at the moment. As I had referenced, these products are moving so quickly that they are moving and adding options and features as they go forward. but the product that we tested did not have the internet connection. And I would probably refer you to the Digi RTU website in order to see if that's available at this time.
And another quick one, does the Digi RTU use a VFD as well as the other products?
The Digi RTU?
Right.
Yeah, the Digi RTU used the VFD on both the compressor and the supply fan. So it used one VFD to control both of those products in tandem. The Catalyst product uses a VFD to only control the supply fan. So they are VFD-based solutions. The premium ventilation does not have any VFD associated with it.
Thank you, Mark. Kind of maybe a bit of a head scratcher, but so why did units that didn't get optimization packages use more energy? Do you have a sense of why that showed up that way?
Well, I think that's something that we definitely need to look into in future research or next steps. I think it's a number of those optimization packages modify the airflow rates that are associated with them, and I think one of the things we deduced from our data was that the total supply air to the space was being modified up and down based on the VFD, at least for the case of the Digi RTU and the Catalyst. But what was not being modified in that space were the exhaust products that were happening in that area. So the same amount of exhaust was going out of the building, but a varying amount of outdoor air was being brought in as a result of the modification or the speed of the supply fans. So that could have ended up causing issues with depressurization and uncontrolled infiltration happening in the space. But that's something we just that's just a hypothesis at this point. We don't have any data that supports that.
Great, and we have a few questions actually that get to this same question. Do you know why the units increase the gas consumption for those that received optimization packages?
Well, I think I just answered that question in the fact that we believe that uncontrolled ventilation or infiltration as a result of the decrease in ventilation, but no increase or decrease in exhaust, which ultimately could have depressurized the space. But again, we did not measure the parameters we needed to make an assessment of that, so it is just a hypothesis at this point.
Thank you. All right, I think we have one or two more questions, and again, keep them coming if you do have more. So you talked about how the different types of buildings, there are RTUs on a lot of different types of buildings. Did you see savings in one building type that were greater versus another building type? Was there any consistency there?
There was no consistent savings that we could identify as a result of building type, but you'll note as a reference from my slide that we had a limited amount of data from the buildings that we measured. There were a lot of them were office type. There were light manufacturing, and there were some small assembly areas and conference rooms. So I don't think we didn't have enough information in order to make an estimate whether there was specific savings attributed to a given building type. I think that's definitely something that needs to be looked at as we go forward.
Excellent. We have a number of questions coming in. Could you maybe say a little bit more about how the savings were estimated? Were the savings normalized or based on ambient conditions and the unit runtime?
So we measured the energy consumption of the unit with a watt meter, and we measured the consumption of the gas with the timing of the gas valve. And so that predicted our savings when we saw it running in a particular Minnesota climate that happened during our monitoring period. We took that information and normalized it to TMY data and looked at the results of the savings as it's applied onto TMY data. The runtime of the units was not normalized. It was the actual runtime of the unit as we saw it in the space. So there was not a lot of capability of projecting that forward, other than as long as the space was similar in runtime, the savings could be attributed across the different building type, or the particular building type that we were looking at.
Great. I think we have time for just 2 more questions. I think you touched briefly on the cost of the optimization packages. I don't know if you wanted to expand on that. There was a question about that, if you had other detail to add.
The cost, again, I referenced 2 different costs. The actual cost that we saw as part of our study could not be characterized as typical, because we had a number of additional equipment and installation requirements that skewed the numbers for the installation. And that's why we developed that small, standard, and large site and asked the manufacturers to give us typical installation costs for those sites. And again, the catalyst and the Digi RTU were supported by the manufacturers, and the premium ventilation was not supported by a manufacturer, so to speak. We did use our estimates from installation of the units, premium ventilation case, and applied that to the 3 different sites. But the thing to note, though, is that premium ventilation definitely requires a lot more run of wire between the thermostat and the rooftop, and there's a wide variety of installation variances that you can't account for in a lot of spaces. So you could have an open plenum ceiling where the wiring would be extremely easy to run, or you could have a very difficult fishing of wire in interior walls that could affect the cost of the premium ventilation. So I wouldn't use those as gospel numbers, other than they are just relative numbers, that you can use going forward.
All right, just one final question, but I also did want to add that we are recording this webinar, and that later this week we'll have both the recording available, and then the slides from today's webinar will go up yet today or tomorrow. So kind of looking out beyond some of the technologies, a question was raised about, is anything being done to discuss potential incentives or ways to help bring these products to market? Those discussions, are they being had with the utilities? Do you know of anything about that, Mark?
Well, I know the utilities are looking to this report, at least the Minnesota utilities are looking to this report to document what are the savings associated with these technologies. And we hope to supply this information to the utilities. I didn't get a chance to reference it, but the report is not out as of right now. We are in the final editing stages of the report. We hope to have the report issued early in 2015. But the goal of that report is to give information to the utilities about what these savings can be on these units in the Minnesota climate. Again, as I referenced in the previous discussion, a lot of the previous savings numbers that are given by manufacturers are in some other climate other than Minnesota. So we wanted to document what are the true savings in the Minnesota climate, and these documented savings numbers will be used by the utilities in order to develop a program that will support the installation of rooftop unit optimization.
Thank you, Mark. This has been a very informative webinar. Appreciate your time, and thank you all for tuning in. As I mentioned earlier, if you are interested in learning more about our research is going on and events. Our free newsletter is a great way to get that information, and we welcome you and invite you to sign up for that on our website. And you can also follow us on Twitter at MNCEE, where the Innovation Exchange helps to share news and ideas on energy policy, technology, and our research at both the local and national level. So thank you again for joining us today, and we hope to see you at future webinars.